Good morning, it's Jeremy. It's Tuesday, May the 19th. Today I'm receiving MSK144 or Meteor Scatter. So I'm looking here at a V dipole, which I've set up for 6 meters. I've been trying to receive a good signal for the past couple of weeks. I've tried various times of the day and various locations, but this morning I was lucky. Around, I think it was 7:58 in the morning, I got a signal from a K2 station down, I think in Florida, which is quite a good distance. And it seems that the meteor scatter is most active in the early morning. But you've got to have a station transmitting at that time, and you've got to have the actual meteors to get a contact. So it's not something you can sort of like instantly, within 5 minutes get a decode. It takes a while. Let's go inside. This is the setup here. I'm using WSJT-X MSK144, and I'm scanning. And if I go over here, I'm receiving with SDR sharp. I've got it tuned to the 6 meter frequency of 50.260 for MSK144. I'm sampling at 250 kilosamples per second. I've got the gain set at 29.7. If you go any more than that, depending on your RTL, you're going to have a problem with overload. So to get the best signal to noise ratio, you have to adjust the gain. And in this particular case, it's 29.7 dB. And I've got it set at USB 5 kilohertz. And the audio is piped over using VB cable. This is the decode I got this morning. It was a CQ from a K2 station down in Florida. So we're going to go over to the blog post and we'll look at some more details of the MSK144 protocol. Okay, so I've got some more detail in the blog post, so that's just what I'm looking at here. Here's a block diagram of the overall system. So basically what we're trying to do is when we have an incoming flux of meteors, generally it's in the E layer from 80 to 120 kilometers. And the peak seems to be historically from 0500 to 0800, and you get a reflection like that. I'm set up for 6 meters, that's where most of the activity is, and I'm using a V dipole. For the other frequencies, you can use a Yagi, like for instance for the 2 meter and 70 centimeters. So the V dipole feeds an RTL-SDR, which goes into SDR sharp, which is receiving on USB at 6 meters, it would be 50.26 megahertz, and then I go from VB cable over to WSJT-X MSK144. So that's basically the block diagram. Here's a look at PSK Reporter, and it tells you what the activity is like for MSK at 6 meters. You can see a lot of stations down here in the US, not too many in Canada, and there's the activity at 2 meters. So you can see there's a lot more activity at 6 meters, which makes sense. That's because that seems to be historically the best frequency. Down here, I've got a list of the MSK144 parameters. There's a very good reference paper here. This was written by Stephen Franke and Joseph Taylor, Dr. Taylor, K1JT. And it describes the MSK144 protocol, the history, and the various parameters. So that's basically where I got my information. And it gives some waveforms here. So what I've done is I've listed the parameters here. So with minimum shift keying, the data rate is selected to be half the frequency shift is selected to be half the data rate, so you get a nice smooth spectrum. You don't see the mark and space frequencies when you have the MSK. It's just a sin X over X shape. Data rate's 2000 baud. That's about 250 characters per second. It's designed for a USB SSB USB bandwidth of 2500 hertz, and you can have a signal to noise ratio as low as -8 dB. So what I did is I simulated it in Psychos. Here's basically how it works. All the data is compressed down to about 72 bits. That's your call sign, a CQ, etc., whatever you're sending. So that'll be 72 bits. You add an 8-bit CRC. So that's 80 bits. And then to that, you add 48 bits of forward error correction. So an LDPC is a low-density parity check coder. So you have 128 bits total.
And then you break that down into two chunks, the first chunk at 48, the second chunk at 80. And then between those two chunks, you stick an 8-bit sync byte. So that's basically what the frame looks like. So I've simulated the frame using Psychos. I'm just following the protocol in that paper. And I've created the data in Psychos Lab as a script file, and I'm reading it in as a structure here. So I've chosen my data, the first 17 bits, to match exactly what was in the paper. So if you look at figure 1 in reference 3, you'll see that the I and Q data look like that. And in my simulation here, that's the same thing I have. So there's the I data, there's the Q data, and those are the half sine pulses. You can see the spectrum is nice and smooth here. And then finally down here, there's my successful reception of the K2 station down in EL99. That's the Maidenhead grid. So that's just a review of what I have in the blog post.